My dear students, in this lecture we are going to discuss about Jacobi and Gauss-Seidel iterative methods, which are used to solve the linear equations of n variables in general. The basic procedure of the method is the following. Algebraically solve each linear equation for xi. Assume an initial guess solution array. Solve for each xi and repeat. Use absolute relative approximate error after each iteration to check if error is within the specified tolerance. So this is about the Jacobi method in brief. Now consider the set of n equations in n variables. a11x1 plus a12x2 plus a13x3 and so on a1n xn is equal to b1. Similarly, the second equation has a21x1 plus a22x2 and so on a2n xn is equal to b2, and the nth equation is going to be an1x1 plus an2x2 plus an3x3 and so on ann xn is equal to bn. Next, we solve these n equations as follows. x1 is written in terms of other variables. Similarly, x2 is written in terms of other variables and so on. xn is written in terms of other variables. The general form each equation is given as follows. x1 equals b1 minus sigma a1j xj and j is equal to 1, j is not equal to 1 up to n and so on. Similarly, x2, xn minus 1, xn, the general form of each equation is given as follows. Similarly, any ith variable can be given by this general formula bi minus sigma age xj. J is equal to 1, j is not equal to I divided by ai. I is running from 1 to n. So we are here assuming an initial guess in the form of array x1, x2, so on, xn. Calculate the absolute relative approximate error of each iteration. It is given by xi new minus xi old divided by xi new into 100. So this will give you the relative approximate error at each computation of first iteration, second iteration, and so on. So now look at an example. A given system of equations 12x1 plus 3x2 minus 5x3 is equal to 1, x1 plus 5x2 plus 3x3 is equal to 28, 3x1 plus 7x2 plus 3x3 is equal to 76. Its coefficient matrix is given by as 12, 3, minus 5, 1, 5, 3, 3, 7 and 13. And initial guess we're taking as x1 is equal to 1, x2 is equal to 0, x3 is equal to 1. And also here we are checking one condition that the coefficient matrix is diagonally dominant. This means the diagonal elements must be greater than or equal to the sum of the other elements in that particular row. For example, a11 must be greater than or equal to the sum of 3 plus the sum of 5. So that's what here I have 8. A22 is equal to what? 4, and it is going to be greater. 5 is greater than 4, and similarly 13 is greater than 10. Therefore, the given matrix is diagonally dominant. Therefore, we can apply the Jacobi method successfully. So as before, we are writing x1 in terms of x2 and x3, x2 in terms of x1 and x3, x3 in terms of x1 and x2, and therefore we are substituting initial guess 1, 0, 1 in this, and I am getting 0.5 and 4.8 and 5.61. This is the first iteration. Similarly, we can go for the second iteration by substituting these values. Then we can go for third iteration by substituting the values of second iteration, and so on. Therefore, finally, we will get, after 10 iterations, the values of the variable becomes x1 is equal to 0.99919, x2 is equal to 0.3.001, and x3 is equal to 4.001. Approximately, I can take it as x1 is equal to 1, and x2 is equal to 3, and x3 is equal to 4. So this is about Jacobi method. Next, we will go for the next iterative method, which is called Gauss-Siedel method. Again, it is going to be the same procedure. I need not want to repeat the same thing. And why we are doing this Gauss-Seidel method means the Gauss-Seidel method allows users to control round-off error. Elimination methods such as Gauss elimination and LU decomposition are prone to round-off error. Also, if the physics of the problem are understood, a close initial guess can be done, and so on. So as before, the same simultaneous equations we are taking n equations in n variables, and the same thing here I have. Next thing is again the same technique. We are rewriting the equations in terms of x1, x2, x minus 1, and xn in terms of other variables as before, and the general formula for x1, x2, and so on up to xn. And the ith formula is going to be xi is given by, as before, bi minus sigma ij xj divided by ai, and so on. And the same initial guess I am taking as x1, x2, xn minus 1, xn. You take it as the vector, and then as before, we have relative approximate error is calculated using this formula. Again, the system of equations we have and its corresponding quotient matrix is given here, and with an initial guess of x1 is equal to 1, x2 is equal to 0, x3 is equal to 1. And similarly, here also the matrix has to be diagonally dominant, then only it will convergent, otherwise it will be divergent. Therefore, this method is applicable only the given matrix is diagonally dominant, and it is clear that this from this explanation it is clearly diagonally dominant. And you see that here x1, by substituting the here we are substituting the latest values. It's a little bit change over Jacobi method, where we are using only previous iteration values. Here we are using the latest values in calculating the x1, x1, x3. So initially we are taking x1 is equal to, and here I have x2 is substituted as 0 and x3 as 1, and I am getting 0.5. So now we are not going to take x1 as 1, but in the second step I am taking x1 as 0.5. You see that it is the latest value that is available and calculating this. So by doing this way, the convergence is very fast, and when compared to the Jacobi method, this is terminating in within 3 iterations, while as in Jacobi method it is running into 10 iterations. So you see that after first iteration, the error we computed is 61 and 67 point in the case of first variable, 100% in the second variable, and in the third variable 67.662. So again you go for the next iteration, and therefore I am substituting here. I am getting the value 0.14679, 3.7153, 3.818, and so on. So this is after iteration. And if you see the error, it is 2.240, and the first case, and the second variable 31, and third variable 18. So you see that here there is a drastically depreciation in the error we are committing. So therefore, finally, after doing so many 6 iterations, you see that here I am getting the value for x1 is 0.99 and so on, 3.0001, and x3 is 4.001. So approximately the values are going to be x1 is equal to 1, and x2 is equal to 3, and x3 is equal to 4. So therefore here this is what is